All right, here we're going to go ahead and look at 10.6 alternating series and conditional convergence. First thing we want to do is look at this first one here where we just have a basic alternating series here, and we're just going to have n equals 1 for the first term. When n equals 1, we end up with negative 1 squared, which is 1, and then 1 over 1. And then for n equals 2, we end up with negative 1 to the 3, which is going to be negative 1 over 2. So we get a minus 1/2, and then we'll end up with a plus 1/3 and a minus 1/4 and a plus, so on and so forth. Okay, the next one here we have it can actually be written as a geometric series from n equals 1 to infinity, and this is negative 1/2 to the n times 4. Now be careful here, because geometric series, you have a sum on a times r to the n minus 1, and here we don't have that, we just have to the n. So what we could do is look at this and say we have a to the negative 1/2 to the n minus 1. That's what we're looking for. And what we have is 4 times negative 1/2 to the n. And if we cancel this out, we'll be left with a equals 4 times negative 1/2, which is just negative 2. So our actual a value here is negative 2. So when we go to do this, right, because they converge a over 1 minus r, we end up with, when they converge that. And so we end up with negative 2 over 1 minus negative 1/2. And then that's going to equal ultimately negative 4/3. Okay, that's what that one's going to converge to. And then here in the last one, we've got negative 1 to the n plus 1, and that's times n, so we're going to end up with 1 minus 2 plus 3 minus 4, and it's going to turn out one like this is going to diverge. Okay, so let's take a look at the test for this. This is the alternating series test, and when we look at this one, the series that's given here that's alternating like this will converge if the following conditions are satisfied. First, all the UNs, the coefficients, they're all positive. All right, we don't need to be taking the negative of a negative and messing up our nice alternating. So we need to be alternating plus minus, plus minus, plus minus, plus minus. So all the UNs right here are positive. The UNs are eventually non-increasing. So basically, there's a UN greater than or equal to UN plus 1 for all n's that are greater than or equal to some n for some int n. So at some point, the next values stop being greater than the previous one. They stop increasing. All right, and the limit of UN is going to go to 0. Be careful. This is not a test for divergence. This only tells you convergence. So be careful of that. So let's go ahead and look at an example here. Example 1, apply the alternating series test to the harmonic series. So if we look at this, U1 is 1, U2 will end up being 1/2, U3 is 1/3, so on and so forth, such that all the UN are just 1 over n. Okay, and so that's good. So first thing, they're all positive. That's our first thing, and yes. that way we have nice consistent alternating, and we get a nice canceling that you're going to see we need in just a moment. We also need to check, is it non-increasing? Non-increasing for n greater than or equal to 1, and the answer to that is yes. We are consistently we're consistently stepping down every time. 1/2 is less than 1, is 1/3 is less than 1/2, and so on and so forth. And then we need to check the limit. And the limit as n goes to infinity of un is the limit as n goes to infinity 1 over n, and that equals 0. And so we get a nice little check mark there. You could also just un equals 1 over n goes to 0. Okay, so this is good. It converges to some limit, and so therefore this converges. All right, we met all the criteria that were right here, and so we're good. All three of those things converges. So take a look at the pictures here. What you can see is sometimes this alternating series will converge even though the regular series does not. So if we look at this, the harmonic series diverges with partial sums that eventually exceed some value, right? But the alternating version of it here actually will start to converge because we're adding and then taking away and then adding and then taking away, and we can actually converge this down to a value. And if you notice, this is actually this one right here that we did first, and so we can basically write here that the alternating version, the alternating harmonic series converges by our alternating series test, but the harmonic series diverges. Okay? So let's take a look then after that at some conditional convergence. And so definition, we're going to get a series that is convergent but not absolutely convergent. Okay, so some examples here. Harmonic. Okay, we have a sum from n equals 1 to infinity of -1 to the n plus 1, 1 over n, and that converges. Okay, and then sum of n equals 1 to infinity of the absolute value of -1 to the n plus 1 times 1 over n. This will just equal the sum from n equals 1 to infinity of 1 over n, right? Because we're taking the absolute value, so all the positives, the plus minuses, or all the minus signs are going to disappear, and this diverges. Okay? P series. Let P be any positive constant and we get here sum from n equals 1 to infinity of -1 to the n minus 1 over n to the p, and that's going to equal 1 minus 1 over 2 to the p plus 1 over 3 to the p minus 1 over 4 to the p plus dot dot dot. And this thing will converge absolutely if p is greater than 1, and it will converge conditionally if p is greater than 0 but less than or equal to 1. Okay? And taking a look at this, we can do u1, 1 over 1 to the p, u2, 1 over 2 to the p, so on and so forth. Un is equal to 1 over n to the p. If we look at that, we can check it. Is it positive? Yep. Are the un's positive? Is it non-increasing for all n greater than or equal to 1? All right. It's important. P is positive here. And yes, it's non-increasing for everything greater than that. And then 1 over n to the p, that's going to go to 0. So therefore, this converges by AST. Okay? Oh, I meant to put a check mark there. All right, so the next little part here is just some stuff I want to just talk you through real quick. I don't even think there's any homework questions on this, but we'll go ahead and go through it here. Estimating the limit for alternating series, theorem 16. The alternating series estimation theorem. If the alternating series sum from n equals 1 to infinity of -1 to the n plus 1 times un satisfies the three conditions of theorem 15. So that was right here. Basically, we need our three conditions. Then for n greater than or equal to some n, our partial sum here, Sn, is equal to u1 minus u2 plus so on and so forth. And it approximates the sum L of the series with an error whose absolute value is less than u to the n plus 1. So, which is the absolute value of the first unused term. So we're going up to un, and this is the un plus 1. Furthermore, the sum L lies between any successive partial sums Sn and Sn plus 1. Okay? And remember, L minus Sn has the same sign as the first unused term. I'm sorry, and the remainder. I said remember, reading poorly. And then the last thing, just rearranging series here. The rearrangement theorem for absolutely convergent series. If you have a series of ANs summed from n equals 1 to infinity, and it converges absolutely, and then you have B1, B2, Bn is any arrangement of the sequence, the set of all the ANs, so you rearrange them, then Bn converges absolutely, and the two series will equal each other. Okay, and that was pretty much it.